In the parameters, when you're setting this up within the E3 and the iPro, there's something called a condenser type. And in that condenser type, it asks you, do you want differential? So which is a differential temperature. So knowing the TD of your gas cooler, I said it was 10 degrees for subcritical operation. You put that 10-degree set point in there. And under control type, you would say, okay, it's a control type. I want to control based on a temperature, not a pressure. You can control based on a gas cooler out pressure. And because I mentioned that temperature T1 sitting on the outlet of the gas cooler has an impact on the high pressure valve position in subcritical mode and in transcritical mode, and also on the fans trying to maintain that preset TD of 10 degrees. My chart below is really what we went to a job where it was set for pressure set point instead of temperature set point. So your high pressure and your gas coolers were decoupled from one another and were fighting each other off. You can see on the top here, this is my subcooling set point is at 5 degrees, but my control values was jumping, had high subcooling, had low subcooling. My pink down here, my gas cooler outlet temperature was swinging, and my gas cooler outlet pressures were swinging, all because my fans and my high pressure valve were fighting each other off. Yeah. So when we changed it to control type, everything just settled right out. My subcooling was maintained reasonably. Gas cooler outlet temperature settled out, and it was right tracking with ambient, which is the green line. My gas cooler outlet pressure settled, and everything settled out. So it's important to make sure you have that right order of set points in there.
Welcome to CO2 Experts Live. Super excited about this session with my good friend, André Patenaude. We've done tons of podcasts together. We've done a ton of knowledge sessions on CO2, and we continue to learn from each other, continue to grow. Super excited for this conversation because we're going to be diving into the high pressure valve, the iPro. We know we continue to see more and more out there, and we're going to just dive into some technical stuff today. André, how you doing, brother?
Doing great, Trevor. Thanks for having me on again. I really appreciate it.
Oh, man. Well, I always love having our conversations because every time we talk, it can go in a bunch of different directions, deep technical, deep, on CO2 or whatever the topics are, right? Sustainability, energy efficiency. That's why I love our conversations, because they can go really anywhere from design to technical stuff. But today we're going to be diving into the high pressure control because we're seeing more and more. I just finished a CO2 course just before this, and we were actually talking about the iPro because it was on a zero zone rack, and they were like, okay, it's new. How does it work? And then we just dove into it. And this is going to be perfect for all those people out there that are going to start to see them on more and more racks, because they're on Hill Phoenix racks. They're on different racks that manufacturers build here in North America. And we're going to continue to see these controllers out there and grow, especially with the E3. So, André, I'm excited about this conversation.
Thanks. No, so am I, Trevor. And thanks for the opportunity. So I can jump right in here if that's okay with you.
Yeah, let's do it.
Awesome. So iPro, we're going to be talking about that. So I wanted to kind of baseline us here just on this system, because I'm going to be using this system and these colors. So if you're looking at it, I wanted you to understand what that means right away. So the red is always going to be high pressure, medium temp discharge gas or gas cooler outlet. Anytime you see yellow, it's either going to be liquid CO2 or vapor coming off the flash tank. Okay. Green is always medium temp suction, and blue is always low temp suction, just because I've got another chart coming up and I want you to understand what those colors mean without you wasting any time. So if we're going to talk about the high pressure control, we also want to touch on 2 slides on the E3 and its interaction with the system controls. So that's where I want to start before we get to the high pressure control, because the E3 is your supervisory device that's controlling, yes, your compression, gas cooler integration, but also every other component gets tied to it. And more retailers, regardless of the total solution, want to be able to those components to communicate so they can bring that value and understand what's going on overall with their system. Copeland, what we did do a few years ago is we came up with this E3 supervisory control, but specifically with CO2 applications. So what's unique with this is if you use that part number, you don't have to have a special license to add this, that, or the other feature. It's there for you for CO2. So that's what I want to point out.
I remember all the trainings we did with the first generation of the transcritical trainer that we used to use on, and it was an E2, and it did have the high pressure control, you know what I mean? But there was just so many workarounds, flex combiners, all this stuff that you don't need to deal with anymore.
Absolutely, absolutely. And that's what trying to simplify for the application exactly, Trevor. So we've got these preloaded applications I mentioned. There's new suction groups for low temp, medium temp, parallel compression is built into the suction application. We've got liquid injection, hot gas injection. Before, exactly what you said, you had to write a flex combiner in order to manage those. But now you go into the application, you fill in the guidelines. You know, when do you want the liquid injection to be enabled based on a superheat set point? When do you want it to stop? And so on and so forth. The load management, the startup sequence is part of it. Yes, you have to tell which loads to come on, but it's a menu-driven device now. Enable, disable evaporator loads based on certain alarms. These are user-defined, so you can do that specifically. And then you've got some extra monitoring features specifically for CO2. And, you know, when we started with CO2 systems, the oil management, we used to have these solenoid valves injecting all over these individual manifolds. We had up to 20 flex combiners just for that. So we've completely eliminated that in an application, which is kind of nice.
Yeah. And that makes it so much more easier for the startup guys. And I keep telling all the technicians in my training, you got to try to get to a startup at some point, because that's where you're going to learn so much. I was down with Brett Cheshire and Paul Bennett at a startup, and we walked through the whole rack with the E3 and the iPro, and you got to go through it once or twice. We're talking about it here, and Andre is going to show you a lot of stuff, but you got to go actually put your hands on it in the field, and you got to go look at the set points and the parameter setups.
No, absolutely. And if you do have an E3, then you can customize that main screen. You go to your little their home screen there, you pick your RX layout, and boom, you can customize it to have all your CO2 suction groups. You can look at your condensers. You can look at your circuits. The high pressure valve we're going to talk about, this top right corner, you click on the iPro, and I'll show you what that looks like from a layout perspective and a troubleshooting tool, and then all your case controls, and you can even graph. So it's up to you how you want to look at it. So that's kind of right up front, E3, its ability to view that information. Okay. So now we want to drill down exactly what you're interested in here is the high pressure controller and what its function does in a CO2 system, because we didn't have those in HFC system. This is unique to CO2, right? And even though you look at the high pressure valve that's sitting here that is connected to it, well, that's kind of the position that a holdback valve used to be on an HFC system. And sometimes it's used as a holdback valve here. And sometimes it's used, as we'll get into, as just a high pressure expansion valve. But the iPro is connected to the high pressure valve. The bypass gas valve is managing flash tank, and it has interaction with the gas cooler. And that's what I'm going to start talking about first before I drill down, because of the importance of understanding where does a gas cooler fit and how does it play nice with the high pressure valve. Because as we drill into these systems, as we as Copeland troubleshoot these systems, we're finding out that a lot of systems that aren't properly performing is because the gas cooler, high pressure valve were not synced together. They were set up, no fault of the individual if he wasn't properly trained, not to play nice. And I'm going to kind of talk about what does that mean. So what we do understand, and you've done a great job, Trevor, of talking about subcritical modes and transcritical modes in CO2, but I've got a gas cooler here. And what's important, these gas cooler, even within the E3, you can set up a TD within that gas cooler that if you've got a 60-degree ambient, and you can see that ambient temperature sensor there, that gas cooler in subcritical mode will start modulating fans in order to maintain that 10-degree TD, which in turn gives you a 70-degree gas cooler out. I put T1 there because for the iPro, that's called temperature sensor T1. So I'll keep referring to that because it relates back to the iPro. When we're operating in transcritical mode, though, we are not condensing. So the TD is a bit lower on these gas coolers. So you may have 85-degree air entering and you're only desuperheating here. So you're actually desupering a discharge gas, but your gas cooler out goes from an ambient of 85 to a gas cooler out of 92. And the placement of that temperature sensor is important, the ambient temperature sensor, because if you've got an adiabatic gas cooler, you've got to put that sensor close to the coil so we get the actual temperature that the coil is seeing, the air temperature the coil is seeing. So that becomes your your air inlet temperature sensor. So super important. So
the location of that is key. You want to make sure that there's no sun beating on it or there's no reflection. Because I've had a technician say, yeah, we had steel. They had steel feet, so where they put the condenser down on, but it was hitting the steel, reflecting off there onto the ambient sensor, which you would never think of. And all of a sudden, that was changing how that ambient sensor was reacting.
Yeah, that ambient sensor is, as we go through this presentation, is critical. And so, you see here the location, of course, at the outlet of the gas cooler. We want to make sure it's wrapped. It's on a horizontal run. If you've got a A-frame heated gas cooler, you want to make sure that it's at the outlet of that T, so you're getting a mix on a horizontal run, 5 or 7 o'clock on the pipe. Metal clamps, not tie wraps that break over time, thermomastic paste, and waterproof insulation. Not having it so often I've heard it just dangling there in the sun. It's not even on the pipe, right? Yeah. So that's super important. Now, Paul Burnett sent me this picture. What not to do, a tie wrap on the most important sensor on a system that the sun is beating on it, that's affecting fan speed. It's affecting the high pressure valve positioning, as we'll talk about in a sec. So don't do that. Yeah. Super important. The other thing too, I don't know if you can you see my full screen, Trevor? Yep. Because I've got it blocked here in my, maybe, oh, there you go. So when we look at this schematic now, this is a different schematic, but all those colors I talked about originally also apply. And we've got my T1 temperature sensor sitting here at the outlet of my gas cooler. And I said, one of the things that we found out from our field service team, when we went back and did some troubleshooting of CO2 system, we found that something was super important that needed to be followed. In the box down here, it says that the gas cooler minimum pressure set point should be approximately 100 PSI higher than flash tank. So if I'm trying to control 520 PSI in my flash tank, which is 30-degree saturation, that means that my gas cooler minimum should be somewhere around 520 or a little bit higher, minimum 100 pounds. I use 50-degree saturation because it's easy, right?
638 PSI.
About 638 PSI. Yeah. So that, because you don't want the gas cooler pressure to try to get lower than the flash tank. That doesn't make any sense. No, so you want to have it higher, number one. The other thing that we found that wasn't always done is the gas cooler minimum pressure of, in this case, we're saying 638, has to be higher than the minimum high pressure set point. This is all in the winter, right? When it gets cold. Yep. Because we don't want the gas cooler to try to get lower than my minimum high pressure set point, because then they'll fight each other off, okay? And incidentally, my minimum high pressure set point is based on a saturation pressure based on that temperature sensor at the outlet of the gas cooler. My fan speeds are also based on that gas cooler outlet temperature sensor. Two very important points here. And you can see my iPro is connected here to my T1 sensor, my P1 transducer at the outlet of my gas cooler, And my iPro is also connected to a P2 pressure transducer on the flash tank. So important were the parts that are connected. And my XEV here is connected to my bypass gas valve and my high pressure valve. So two important things. So when we're setting up the gas cooler, there's something that's from a critical stable operation here.
Just before we keep going, Andre, back on the last slide. So
sure.
would that be 3 different set points? So we know the flash tank set point is the receiver set point. You input that. I want to run the flash tank receiver at 520 PSI. This example could be 34 bar, doesn't matter. And then we got the minimum set point for the gas cooler, which is 638 PSI or 50 degrees Fahrenheit saturated. Is that a set point? And then 570 PSI is another set point. So is that 3 different set points?
Correct. That's 3 different set points. You've got a minimum gas cooler set point, you've got a minimum high pressure set point, and then you've got your target flash tank set point. Correct.
Okay, great.
Correct.
And inside the iPro, you would set those 3 parameters up, correct?
Correct.
Great.
Yep. Yep. So in the parameters, when you're setting this up within the E3 and the iPro, there's something called a condenser type. And in that condenser type, it asks you, do you want differential? So which is a differential temperature. So knowing the TD of your gas cooler, I said it was 10 degrees for subcritical operation. You put that 10-degree set point in there. And under control type, you would say, okay, it's a control type. I want to control based on a temperature, not a pressure. You can control based on a gas cooler out pressure. And because I mentioned that temperature T1 sitting on the outlet of the gas cooler is both has an impact on the high pressure valve position in subcritical mode and in transcritical mode, and also on the fans trying to maintain that preset TD of 10 degrees. My chart below is really what we went to a job where it was set for pressure set point instead of temperature set point. So your high pressure and your gas coolers were decoupled from one another and were fighting each other off. And you can see on the top here, this is my subcooling set point is at 5 degrees, but my control values was jumping, had high subcooling, had low subcooling. My pink down here, my gas cooler outlet temperature was swinging, and my gas cooler outlet pressures were swinging, all because my fans and my high pressure valve were fighting each other off. Yeah. So when we changed it to control type, everything just settled right out. My subcooling was maintained reasonably. Gas cooler outlet temperature settled out. And it was right tracking with ambient, which is the green line. My gas cooler outlet pressure settled and everything settled out. So it's important to make sure you have that right order of set points in there. So
and what the graph you showed there is so important as a technician. So anybody listening on the podcast, so it's the trend graphs. You got to go in and look at those different trend graphs. As you see with Andre's slide, he had the percentage of the valve open. He had the fans on and off and the percentage of their speeds. You have to be looking at that, as well as the temperature, the drop leg center, and you got to plot that stuff. This is how you troubleshoot from remotely or at a site. You got to look at what happened and what you need to do to remedy that. And sometimes this takes a while, right? That didn't happen overnight to figure that out. You know, they tried and their top guys from the company were out there working on that, learning this as it goes. So you got to spend some time on those trend graphs and learn those.
No, you're absolutely right. And you have the flexibility within the E3 to take any graph that you want to look at and layer them one over the other with the exact same timestamp. So you can see a spike here may have been a reaction from this valve not opening or opening too much and vice versa. So it's really important once you get to know it, how to use it as a good troubleshooting tool, as you mentioned, Trevor. So if we take a look here and to spend a minute on this chart talking about the high pressure controller, and I mentioned it's controlling the high pressure valve. There's a flash tank set point. There's also a bypass valve set point, which is driven from the flash tank. And I mentioned the gas cooler. So the iPro determines which mode of operation it needs to be in based on that gas cooler outlet temperature sensor. So it's sending that T1, sensing that T1 sensor, and it knows, okay, I need to operate subcritical mode. And I'll talk about what that is in a minute. It manages the high pressure valve, the bypass valve, but it also looks to find out, is there some gas cooler bypass control going on in very low ambient? And I'll show you what that looks like in a minute and how it switches from one temperature sensor to another. It also looks at heat reclaim mode. So all that is integrated within the iPro to maintain some of its functionality. I mentioned in this particular chart, I've got all other components that you'd find in a normal system other than heat exchangers. I didn't want to add heat exchangers to confuse things, but I've got an oil management system there as well. I've got hot gas dump valves. I've got liquid injection valves. Well, when you think about a high pressure valve in a CO2 system, two real modes of operation. If we've got 1,500 pounds of inlet pressure, that's about 104-degree gas cooler out temperature sensor. And I know that based on a table that I'll show you in a few minutes. But if that temperature sensor senses it's about 104 degrees, the high pressure valve will position itself based on the iPro signal to hold back to about 1,500 PSI, because it's the most efficient pressure position to be at when you're operating in transcritical mode. We call it optimized COP. But when you've got 1,500 pounds of pressure on the inlet and you're trying to get 520 in the flash tank, there's almost 1,000 pounds of pressure drop through that thing. It's going to create a ton of flash gas because you have to transfer all that high pressure energy down to 500 pounds. So a lot of energy transfer and flashing that occurs. Because of that, this bypass gas valve is set based on a 520 set point. So if you've got a lot of flash gas in that flash tank, the bypass gas valve will be open a much larger percentage and allow mass flow into my medium temp suction. On the hottest anticipated day in the summer, if you've got a 6 compressor rack medium temp, 3 of those compressors will be running just to manage that bypass flash gas. And those are the taxes you have to pay during high ambient operation. You can think of it as a tax. But when it's cold out and I only have 730 pounds or 60-degree saturation, so you can see the diagram on the left here, I have much less pressure drop. It's only 200 pounds. I'm not creating that much flash gas. My bypass valve is not opening very much to trim the flash tank pressure. So my system is much more efficient because I've got less compressors running here to manage that flash gas. I may not even have any. You could be operating like a normal HFC system almost, because you're coming from the gas cooler through the high pressure valve, very little flash gas, extra flash gas in my flash tank to get down to 520. So that's important to understand the difference. But that high pressure valve sees 100% of the mass flow. So it can get plugged up with dirt. If you've got a coalescent oil filter that breaks apart, all that dirt's going to end up in that valve. You got to make sure that that valve gets cleaned up and properly serviced, or have filters ahead of it. That's super important. There's just another picture of types of dirt that can end up in the inlet strainers of these valves and completely shut them up, because they manage 100% of the gas of the mass flow of the system.
So yeah, this is a really good point for technicians out there. The most important things on those 6 months or year maintenance is going in these high pressure valves and these systems. And you got to be done anyway. Is checking these strainers, pumping down the rack. You got to pump it down properly, know how to isolate it safely, and open these up. You need the gasket kits for them. You can't just open them up and not have the parts for them. You need the other parts for them. And then you got to check the sensors. That gas cooler out sensor that he talked about, the receiver pressure sensor, the ambient sensor, and the temperature probe. You actually have to do the test. have the high pressure gauges. A lot of times there's an analog gauge on there, and you got to do, these are the verifications you have to do almost every time. Because most of the calls that I've taken or people called up and say, I'm running into an issue, is related to the high pressure controller or high pressure valve. The pop off, just because your flash tank has a relief situation or a pop off, a lot of that will have to do a lot of the times with the high pressure valve or the bypass valve, how they're working.
No, good point, Trevor. So this is just a point I wanted to point out. The Copeland has a high pressure valve, but the thing I wanted to point out with this valve, it can use high pressure bypass valve or any other application. But sometimes what we find is that when we ship these to site, they're supposed to be at 50% open. And if for some reason the OEM kind of drove them closed, it gets to the site and then you want to pull a vacuum on them, you need to disconnect the power before you pull a vacuum, because if that motor is powered, you will burn it out. So drive the valve open, disconnect the plug from it, pull your vacuum, and then you can reconnect it after your vacuum's completed and you've got some your vapor charge in there. So you don't want to damage a valve for no reason. The other thing, when you are setting up these valves, you need to make sure, whether it's a Copeland valve, a Danfoss, a Carrel, a Sporlan, it doesn't matter. You've got to make sure you have all the right settings. Is it a bipolar valve? How many steps per second do you drive it? What if it's amperage? All of that data needs to be loaded into the program so that you're getting the movement that you expect with a input going to the valve. If you don't have that, you're going to run into problems. So make sure you pull that information. Super important.
That's a really good point. I had someone call me about a month or two ago and said they have anti-relief, keeps leaking. It keeps bleeding out. And I think there was a CDS valve that they had on the anti-relief. So this is before the pressure relief goes, it'd be like a burp valve. I remember Andre at the ILC, there was a burp valve on that cascade system.
Yeah, absolutely.
We call it burp valve anti-relief, but they're asking me like, we don't know why it continues to leak and it won't 100% shut. And this is exactly what Andre's talking about. They had the wrong step. Instead of 2,500, I think it was 63 something on those CDS valve, and it just kept leaking out. So they always had to keep going charge gas every couple of months. And they're like, what's going on? Exactly what Andre's talking about here. But this is even more important because this controls how that valve will open and close. If you change the speed rate up or the holding current, even though as technicians, this is stuff that we don't really deal with, but this is stuff that we need to check to verify, is this what's causing that valve to act up?
Absolutely. And some have some oversteps to make sure that it's properly seated when they get to the end. So you want to understand how many oversteps to be able to do that without damaging the valve. Yeah, absolutely. So when we take a look at these temperature sensors, I mentioned that the iPro high pressure control has a T1 temperature sensor, gas cooler out, a P1 pressure transducer, which is fairly close to that T1 sensor. You don't want it 20 feet below where you've got actually head coming down and you've got a couple of extra pounds of pressure higher than it thinks it really is when it actually is at the outlet of the gas cooler. Because P1 and T1 are the sensors that are measuring subcooling set points and adjusting a valve. So you want to make sure that your pressure and temperature are as close to saturation as possible so you can drive the valve effectively. P2 is your flash tank pressure transducer. So based on the temperature it sends at the outlet of the gas cooler, the iPro will decide if I'm operating in a subcritical operation or transcritical operation. And when it's operating in a subcritical operation, it's typically maintaining around a 5 degrees of subcooling. It could be 3, it could be whatever you decide, but typically it's around 5 degrees. When it's operating in transcritical mode, so when that gas cooler outlet temperature sensor senses 87 degrees or higher, it switches to a transcritical mode. Now it's operating to an optimal COP. It matches the right pressure to the gas cooler out temperature to optimize efficiency, which I'll show you what that table looks like in a few minutes. But obviously what's super important here is, again, the gas cooler minimum pressure must be greater than my high pressure valve's minimum set point, so they don't fight each other. They stay in balance. Super important. So the iPro, and I've got kind of what I just said there is kind of graphics on the left. So we've got a P1 connected to it, gas cooler out pressure, T1 gas cooler out temp. As I mentioned, P2 pressure sensor for the flash tank, determines the mode, optimize COP for heat for transcritical, has a heat reclaim mode. It is integrated to our E3. If you lose, it also operates as a standalone control should something happen. It can still control the high pressure bypass valve in those set points. We recommend 24 volt DC for the iPro, not necessary, but we do recommend it. Seems to work better with 24 DC. And there's a version code. We just recently updated the version to 4.0. So if you want to find out what that version is, it's written there on the side of the control. So,
and that can't be updated, right? Software can be updated, but firmware can't be updated on these controllers?
That's correct.
Okay.
That's correct. And, you know, we learn as we go, like with any product, right? That's why we recently released that, because we found better ways of managing transitions and so on. So we make tweaks to it, we add a revision, and the way we go.
Yep.
So that's really what we're doing. There was two components to the high pressure system, right? The main brains, if you will, which is the iPro, and then the valve driver, which is what I'm showing here, the XEV20D. And it's connected to valve 1, which is the high pressure valve, and valve 2, which is the bypass valve. And they communicate via LAN, which I'll show you in a minute. 24 volt AC, we prefer your power because it gives you a bit more power when you're driving valves using 24 AC. And we do have a super cap that in case of a power failure, you want to make sure your valves get closed. So this super cap allows you the ability to drive those valve closed in case of a power outage. So quickly, I've got the iPro on the left. I've got the valve driver on the right. And you can see here, 24 volt DC is recommended in the left side here, communicates via LAN. We go to the valve driver. Valve number 1 is my high pressure valve. Here it's called back pressure valve, but we call it high pressure valve. It does both. And valve 2 is my bypass gas valve. I've got all my valve signals, stepper 1, stepper 2, alarms, low pressure alarms, and so on built in. So that kind of gives you a quick diagram. Down here, we have what's called a Visiograph. I'll talk a little bit more about the Visiograph. It is a device where you can actually locally program the iPro. If you don't have the E3 online yet, you can program it through the Visiograph. So that's kind of another device that we can use. When you look at simplicity, what we found out lately, though, is that this high pressure control system, a lot of end users are requesting dual temperature sensors, dual T1 sensors, dual P1 sensors, and dual P2 liquid receiver or flash tank sensors. For redundancy, should something happen, you've got that backup there that you can transfer over. So that's something that we're seeing more and more on systems as they're set up.
So if we go back to the other slide where we had the iPro and the XEV20D. So what's really happened, the brains of the operation is in the iPro. So it's taking the gas cooler pressure, the receiver pressure, the outlet temperature, gas cooler outlet temperature. So it's calculating all that in the calculations inside there. And then between your server port, it's sending that signal to there to say, open the valve and close the valve. So that's So it's just a base, the E22D is just kind of like the base to receive the information from the iPro, correct?
Yeah, we call it a dummy driver. You know, we also have another one, another version from our Alco Europe that could also be used. But you're absolutely right, Trevor. The iPro Small has got all the algorithms built in there and the table that I'm going to show you to optimize COP based on a gas cooler out temperature sensor. The subcooling set point that we set, whether it's 3 degrees or 5 degrees, let's say 5 degrees for simplistic sake, it's in there. And all those operations to maintain that subcooling set point is built into the algorithm, into the iPro. And all it's doing is telling the XEV, position that valve to X, position that valve to Y to maintain the set points that I need. Absolutely.
Yeah. And so just to be clear for everyone, there's no parameters you need to set for the XEV 20. That's, once again, it's all in the iPro. Is that correct?
Correct. All you need to do is give the right voltage, connect the valve to the right points, and you're good to go.
Yeah. And like every other controller, like Dixel or any other manufacturers, you can take your meter and you can put it on the windings and you can actually see the DC voltage changes to see if it's moving or not. And it's going really, really fast. But this is a test as a technician. You go out there and you put your meter, you got to get your meter out on this stuff. And am I actually getting voltage out to that valve? Because the valve is moving or not. So that's just a tip there.
Oh, great point. So as I mentioned, if you're integrated into the E3 and you go to the high pressure section, this is the kind of information you can get. What's my T1 temperature sensor at the gas cooler outlet measuring? It's 82 degrees. Oh, I'm on subcritical mode. What's my set point? It's 5 degrees. Oh, I'm measuring 2 degrees right now, but my set point's 5. What's my pressure? It's 1,012 pounds. My percentage valve open. So my high pressure valve is at 53%. If it's sitting at 100%, you got a problem.
Yeah, definitely.
Or sitting at 0%, your system's off because it's closed. Bypass valve. So my flash tank here is set for 500 pounds. I'm actually at 499.5. And my bypass valve is open 52%. So that's the kind of stuff you can get, and you can graph it. You can graph it by the hour, by the day, by the week, by the month for troubleshooting purposes. So that's what it looks like. Yeah,
that's real important. I love those graphs. What are your thoughts of having, if it's in transcritical or subcritical on there? Because I'm really thinking now, does that really matter? Because it's all done in the background.
You're right.
You know what I mean? Like I think a lot of technicians get confused. Well, it says it's in transcritical or if it's in subcritical and they see it on there. I really think that, to me, that doesn't matter. I know it's really warm out there. That's a day it's in transcritical. We know if it's really cold in the middle of the winter time, it's not going to be in transcritical. So everyone takes it a little bit differently. That, to me, doesn't really matter if it says is that. You got to understand what the temperature is, what that drop leg temperatures, like Andre keeps saying, how important that is. That's what you got to know. Is that at 94 degrees or is that at 60 degrees coming down the drop leg?
Sure. No, that makes perfect sense from a technician's perspective. You know, the system's operating. I mean, you've been around systems. You might not even know it's in transcritical mode or subcritical mode. You're in the machine room. You don't really know what it is unless you look at the pressures. But inside, there's a lot of, if you're in transcritical mode, it is a little simpler because once you hit about 80-degree gas cooler out, that's pretty much the set point that says, all your fans go full speed. When I'm at an 80-degree gas cooler out, we want all those fans to be at full speed because when we do transition into transcritical at 87, they're already operating at full speed. So then all the high pressure valve has to do is maintain the optimum, close or open to maintain an optimum pressure. So transcritical mode is kind of easier, if you will. Subcritical, there's more things going on because now you got fans are cycling or modulating to maintain a TD, number one. They have a minimum to respect, number two. The high pressure valve has a minimum to respect, but the high pressure valve is also maintaining a subcooling set point. Now, there's two ways of getting subcooling at the outlet of a gas cooler. If I'm measuring 60-degree gas cooler out temperature sensor, and that's equivalent to saturation of 733 pounds, there's two ways to get subcooling. I can mechanically reduce the temperature by having a mechanical subcooler at the outlet. That's one way. or I can increase the pressure, which throws me in a subcooling range. Those are two ways. Well, on this system, we don't have a mechanical subcooler at the outlet. So if I want to maintain a subcooling, the high pressure valve closes to build up pressure to throw that liquid into a subcooled region. So if it's measuring 60-degree gas cooler out, it's going to increase the pressure to 784 pounds, which is equivalent to 65 saturation, gaining you 5 degrees subcooling. That's what it's doing. So I just wanted to point that out.
And that's very important to understand, because this goes back to refrigeration 101. What's subcooling? What's superheat? Right. And that
absolutely.
And it doesn't change just because of CO2. It doesn't change. Maybe it's working a little bit differently because we got a high pressure valve that's doing it, but that's the controller inside. And these are just set points that you will set up, which is great. Now it's super easy to set them up, and the controller takes care of it. You just have to check it and verify it with your gauges and temperature probes.
Right. And if you live in a part of the country that gets really, really cold, and even though you've got a minimum gas cooler set point, let's say I've said it was 50 degrees, and all your fans are at minimum speed or off, and the pressure continues to drop, what do? Well, some manufacturers are actually adding a gas bypass around the gas cooler. So they've got a three-way modulated valve that runs off a 0 to 10 volt signal, that as the pressure starts to encroach on that minimum, we want to maintain it. So we're going to bypass a bit of discharge gas to maintain that minimum 50-degree saturation. But when that enable signals goes to the bypass valve, the iPro will switch from T1 to T2 temperature sensor. So now it gets a mix of both gas cooler out and discharge gas bypass. And that's just done, it's just integrated within the control to maintain the level of order in pressures, even though it's very cold outside.
And inside the controller, you have to enable that feature, right? The bypass feature, it has to be enabled so it recognizes T2.
Yeah, exactly. Then you have to, right. Then you've got to recognize T2 and connect it to the right component, the right section of the control. Absolutely. Yep. Great point.
And this comes back in, like I'm just doing like that CO2 course. We bring up the iPro manual. It's only 55 pages. Is it tough? Yes. Reading is tough. Read manuals in general is tough. All of them.
Yeah.
And when you look at, it's 54 pages, but actually it's only like 10 or 15 pages you actually have to read, if that. Right. You don't have to read all the pages. Just get into the set points and understand how the sequence works, just like Andre talked about. That's the most important part.
And once you get that, and you open up the page within the tabs in the E3, I mean, you're filling in the blanks because you understand what you need to fill in.
Or hit the question mark too, because every question mark will tell you exactly what each one of those points on the E3 does.
Which is a great feature. You're absolutely right. Absolutely right. So I'm going to jump over this because I talked some about that. I want to talk a little bit about optimized COP. In your transcritical mode, that gas cooler out temperature sensor T1 will try to position itself to point 2 along a specific isomer here at a specific point of pressure. So this table is built into the iPro. So when we're above 87.8 degrees, it tries to meet a specific temperature. So if I'm at 87.8, it's going to try to position the valve to maintain 1,035 pounds. If it's at 104-degree gas cooler outlet, it's going to try to position the valve to around 1,500 pounds. That's the most optimum point. But one thing that's unique about a CO2 system operating in transcritical mode, because the temperatures and pressures are decoupled, if you at point 2 and you get a busload of people that show up in a store, all the doors get open and the load drives up, even though your compressor, your suctions are pretty high. If you're operating envelope and you still have room to refrigerate, the iPro will start cranking up the head pressure in order to drive additional net refrigeration effect temporarily. And then when the loads start coming back down, it'll reposition itself to the optimum CO2 point, something a little bit unique with CO2. But that table is contained within that iPro.
Yeah, and I learned something yesterday about the enthalpy diagram. So those dotted lines inside the curve, in the bell curve, we know that's 2 phases, but the dotted lines that go up is flash gas percentage. So as you push that, because you always want to go left, as far left as possible, that means you got less flash gas, you got more liquid. My good friend Nabil Cook explained that to me because I didn't really understand, because I knew you got to move it over, it moves it more to the left, but there's actually lines on there to tell you exactly what percentage of flash gas is coming out of your high pressure valve. And that's really what the iPro is doing. It's looking at the percentage of flash gas and moving it up and down, like Andre said. So that's
right. So here, when we're looking at point 2, we've got 10%, 20, 30, 40, 50.
Exactly.
Here, it's almost 60% flash gas. But then we went from 60 down to 35.
Yeah, that's a huge drop.
You paid less taxes, right?
Yeah. And that's how you can read it off enthalpy diagrams. It's that was like eyes wide open when he told me that. I'm like, wow, that's awesome.
Yeah, that's a good way of looking at it. And so I mentioned you can set up the high pressure, the bypass valve using the Visiograph. Maybe not a great picture of the Visiograph here, but it's menu driven, and you can set all those parameters there. If you are hooked up to the E3 and communicating the iPro to the E3, you can only view through here. You can't make adjustments anymore. The adjustments have to be done through the E3. So a little bit different setup, but it's there to help. And the last thing I wanted to mention, Trevor, is the flash tank management. I mean, depending on the design, it's somewhere between 30 to 40 degree flash tank, and your pressures, depending on the OEM, can be somewhere from 475 to 550 pounds. Yeah. But that flash tank is super important because it's got liquid, it's got vapor, it's got flash tank gas coming off of it. You got high pressure vapor coming in from the high pressure valve. A lot of stuff going on within this receiver.
Hot gas defrost, or it could be going back in there return. Like there's so
many. So you can imagine when you're looking at a flash tank that has all of this vapor coming in, vapor coming out, something else to really be concerned about or aware of is a lot of these oil systems will pressure equalize to your flash tank. And you're trying to maintain 520 in an oil reservoir. If your flash tank is not properly managed and you go from maybe 580 to 450 pounds, guess what? Your oil reservoir pressure is also moving from 580 to 450 pounds. Yep. And if you've got some medium temp floating suction happening at the same time and your reservoir pressures drop to 450, you will not have enough differential across your oil level control to flow within that 120 seconds, and then it'll alarm. So these are things you need to look at that might not, you may be thinking it's related to oil, but take a look at other areas of the system that may have impacted oil flow, because we know that in refrigeration system flow, you need pressure for flow to occur, even in an oil system. So those are things that you may just want to take a look at.
Definitely, because now when you get real low load application in the middle of winter, all the curtains are down, the low temp system cycles off, and there is nothing in that flash tank. There's no load coming back to it. Right. That's when you're going to start to see this. This is what I really learned too. I used to think, oh, it's the high side, the summer where systems act up for CO2. No, it's the middle of the winter when it's the coldest day and everything's running great and everything shuts off and it's isolated. That's where the problems usually happen. And you got to think outside the box. You got to look at those trend graphs. Look at your suction, just like Andre said. Well, if my suction is floating suction, well, we're normally running at 410, but we were able to get another 5 psi or 8 psi higher in my suction. But now my receiver or my oil reservoir is down to 530. There's not flow going to happen. So this is something we as technicians may have to limp along till the next day until it warms up and then figure out what caused it. It could be some dirty strainers or something that needs to be cleaned a little bit more. They could be plugging up a bit, and that differential, it's low, but that just made it worse, right? Having dirty filters or inlet filters, things like that.
Yeah, no, absolutely. And flash tank pressure, of course, it's just like a receiver pressure in an HFC system because it is a receiver. So if its pressure is really, really low, then of course the pressure drop across all the expansion valves on your system is very, very low.
Yep.
That means its flow rate is lower and it superheats higher. So things are interrelated. So on an HFC or a CO2 system, you got to think about that inlet pressure, liquid quality, and its impact it have on other parts of the system.
Yeah. And there are going to be systems out there where you're going to see some sort of bypass right into that flash tank. I've seen it in lots of industrial stuff where the load gets so low, they need to inject some gas in there to keep that pressure up. So there's differential across the EVs for those walk-in box that are still running or big distribution warehouses that are still running. So you got to get in and understand the controllers. All that will be in the E3. And you just got to go look and check of all those sequence of operations to make sure, okay, well, when my flash tank gets to this pressure, this solenoid valve will open and inject. But you got to work with the manufacturers who designed this equipment. Andre's here talking about components that they make. The manufacturer will buy them and integrate them into their system. So working with Copeland, working with the manufacturers of the equipment is very, very important to understand these sequence, because what we talk about here are kind of the terms that you see Andre gives ranges. You got to go to that manufacturers to where they specifically say, is it a 650 minimum? Is it a 700 PSI minimum? Is it a 750 minimum for their design?
Right. No, absolutely right, Trevor. So that Trevor, this is kind of the last slide I had because I know we were on a time limit here, so I didn't want to overflow the time here. But
no. This is beautiful. Like, any final thoughts? Well, like, what are your thoughts? Because you're working with contractors all over the world. You're seeing technicians. You got field guys out there, a growing team. So what are some of the things for technicians who may come across this and see? Well, they will come across, start to see these components from the E3, the iPro, or even the compressors or electronics that you guys have.
Yeah, no, you're right. We're in a unique position because we do work with all of these industry professionals, right? And so we're learning a ton about CO2, about integration, about what customers want from a system insights perspective. And at the end of the day, we're just trying to make sure that we learn as much as we can and communicate to the industry so that we can increase adoption of these sustainable solutions a lot faster. So we are staying very close to, everybody from consultants to contractors to our OEMs and end users in any way that we can. But so
awesome.
That's
Andre,
what we're
how can
trying to
people
do.
find out more about you or find more about Copeland?
Trevor, you can go to, there's a lot of information on Copeland E360 Resource Hub. There's videos, there's white papers, there's articles, and we continue to add content on CO2, but also on A2L, on propane, on all of these new sustainable solutions and regulatory conditions that are happening. So go there and you'll find a lot of good stuff.
Andre, once again, thank you so much. I learned a ton from you today. And once again, take this knowledge and share it. Learn from it. Get out there, use your tools, play around with it, check the trend graph. This is the only way you're going to get better, is actually taking the knowledge that you learned today and applying it in the field. Next week, we got another great CO2 expert, Paul Bennett, will be on the show. So come back next week. We're going to dive into field startup. We'll even talk about some of this stuff. This stuff is important for you to learn, to grow your knowledge. Andre, thank you once again. I really appreciate your time. I look forward to the next time we chat.